Okay, so good morning. So first talk of the session will be given by Vinay Kumar on gauge theory assisted radio interferometry, a numerical study.
Hi, I hope you guys can hear me. Good morning to everyone. Thank you for being here. And I thank the organizers for giving me this opportunity to speak about some work I have been doing with Rajaram over the past 3 months. So yeah, let's get into it. So I believe most of you have seen this image. This is an image of M87, which is believed to be a supermassive black hole. This photograph was taken by the EST collaboration in radio frequency. And the colors here represent the intensity of the source, and the striations in the photo represent the direction of polarization. So such photographs are important for people to understand the environment around black holes and study more extreme physics that goes on around black holes. But the process of going from the data we receive to reconstructing this image is a highly difficult process because of various factors. One of them are some corruptions which happen because of non-ideal measurements or because of atmospheric effects. And today's talk will be on how, on one prescription to get rid of these spurious effects. So let's get into it. I'll start with introducing interferometry a bit. So this is a typical interferometric diagram. You have a sky plane, which is mapped out by these L and M coordinates. They're possibly called named latitude and meridian. And in the sky, you have an intensity distribution, which is given by ILM. And corresponding to that, you have a UV plane wherein your telescopes are, which measure electric fields coming from the sky. So on the source, you have electric fields in the LM plane, EX and EY. I will not be talking about EZ, where Z is the line of sight direction, because we can't measure that anyway. These EX and EY are actually complex numbers. And what you receive is small e here, and again, two components EX and EY, both complex numbers. The properties of the source, the polarization property of the source, are encoded in these Stokes parameters defined as such. And these Stokes parameters are related to what are called Stokes visibilities, which you can measure on the Earth by a simple and in principle invertible Fourier transforms. I've not shown the exact nature of the Fourier transform here because it's not required for the talk. And as you can see, these Stokes visibilities are constructed completely out of things that we receive on the Earth. I just need this matrix E1, E2 dagger to construct all these Stokes visibilities and in principle get back the Stokes parameters. So I'll start talking about this matrix now. That matrix is called the coherency matrix. And it is this matrix that gets corrupted due to various factors I mentioned earlier, like atmospheric effects and non-ideal measurement. And this corruption takes place on the electric fields by it sort of multiplies the electric field by a 2x2 matrix with complex entries. So the corruption in the matrix, in the coherency matrix, is then given like this. Now, the idea is that we want to construct quantities which do not depend on these corruptions and which I'll call invariants. And these quantities will then actually represent what is up there in the sky. So let's try to find out how many such invariants can be there. So simple combinatorics tells me that the number of measured quantities is given by 4n square minus 4n. And the number of gain dependent parameters are given by 8n minus 1. This one is there because these gains are actually, you can multiply all the gains by a common phase factor and the output will still be the same. So the total number of invariants is then this. So now how do we construct these invariants? We follow a prescription given by Sam, Rajaram, who are here, and their collaborator Nityanandan, who is in Australia. And yeah, let's see how we do that. So we consider that these gains are actually local gauge transformations, and we make a network of such antennas. So ABC here are antennas, and GA, GB, GC are the local gauge transformations, which are the local gains. We choose a base point A, and then we parallel transport along 3 vertex loops, 3 vertex so-called Wilson loops, which effectively measures curvature. And this can be used to generate gauge invariant quantities. So we define something called advariant first. These advariants are given like this, where the hatted operation is a dagger inverse. This is there because in usual gauge theories where where the gauge group is a unitary group, the inverses and daggers actually are the same thing, but here they are not. So we have to add this hat operation on the middle matrix. As a result, the advariant transforms under gauge transformation as follows. And of these, you can see that some terms cancel off, and you're actually left with just this. This is very interesting because the gauge transformation of the advariant just depends on the local gains at just one element of your array. So this is very interesting and can be used to construct these quantities. So what we do is that we decompose this advariant in terms of the Pauli matrices, and that gives me a 4 vector. And this 4 vector is actually the Stokes visibilities. So, but these are 4 vectors with complex entries. So we split them into the real and complex parts and get 2 4 vectors per advariant. Now under gauge transformations, these 4 vectors can undergo 2 things. They can either be scaled by a factor, or they can undergo Lorentz transformations. If I take Minkowski dot products of these 4 vectors, they'll be Lorentz invariant. So that is one trick we use. And then we see that the number of linearly independent Minkowski dot products can be given by some number like this. Now these all are invariant up to the scale factor I mentioned earlier. So if we rescale by any one of them or by a norm, we get the invariants, which I denote as I tilde. Now, if you do again a number check, you actually get that the number of invariants actually matches with what we predicted by the first argument. So now this was the prescription that was given, and now I perform numerical checks on this prescription. So to perform numerical checks, what we do is that we take the telescopes that are part of the EHT. We, as the Earth rotates, some of these telescopes will be able to look at the M87 black hole, some of them won't be able to look at it. So we record whenever each telescope can actually see M87. We mark these tracks in the corresponding UV plane. So this is how the tracks look like. And then we create a test object in the sky at M87 with some model parameters. It's a very simple object right now because this is very preliminary stage of work. And then we generate data at corresponding UV sites using the Fourier transforms. And we corrupt this data with the gains, which are random matrices. And then we construct invariants as described. So this is how the invariants look. For a 5 antenna array, I have 41 invariants. I have plotted 42 here because I mean they're all scaled out. So they're total 42 in number here. And you can see that with gains and without gains, the invariants are actually matching. So invariants are invariant. Then some more numerical tests were performed. We added additive noise to all these visibilities with an SNR of 35, which is a value close to the lower bound taken from the EHT paper, and over 5,000 realizations. The red line here shows the mean of these invariants, and the blue shows the spread, which is the standard deviation. So you can see that some of them are very closely, very well resolved, while others are not. So we just plotted the distribution of some of these invariants to see what kind of distributions there are. So we added Gaussian noise, and we actually get some invariants as Gaussian distributions, some as highly non-Gaussian distributions. This one here is constrained particularly well, but is non-Gaussian. It has a mean of 0.73 and a standard deviation of 0.05. Compare that with this one, where the mean is around 1.6 and the standard deviation is half of that. This is very poorly constrained. This is sort of well constrained, but both of those are non-Gaussian. This is particularly almost Gaussian, and constrained also good, I would say, not very well. This is one thing we did. The other thing which we wish to do is that we wish to construct Jacobian matrices by seeing how these invariants depend on the model parameters, which would then be, if there are n invariants and m model parameters, it will be a n cross m matrix. And we wish to perform SVD, singular value decomposition, to see which invariants are affected by which model parameters. And this would be essential for parameter estimation, but this is still a work in progress. And there are some limitations to this which we wish to think about in the future. One thing is that if these gains, which were modeled as 2x2 matrices with complex entries, I took them to be invertible, part of GL2C, but I mean, physically, nothing stops them from having a very small determinant or a determinant very close to 0. So that would cause numerical problems and probably problems in theory as well, because inverses are not well defined. So we don't know how to deal with this as of now in this prescription. The other thing obviously is reconstructing the image. We don't know as of now how to go back from the invariants we get to deconstructing the image. So yeah, that's where I land. Thank you for your time.
So any questions?
You are, but I guess people are online, so maybe we should.
So you talked about this non-Gaussian distributions, and you said that some of them are more non-Gaussian than others.
Mhm.
So just curious, means how do you say that which one is more non-Gaussian?
So we look at the skewness and the kurtosis of the distributions, which are well defined in literature and so on. And the skewness for a Gaussian distribution should be close to 0. For a pure Gaussian, it will be 0. And we see that these values are not close to 0.
So this actually is somehow limited up to the fourth moment.
I don't know what the foot movement is.
No, because this the kurtosis is there. So this is up to fourth moment. So you don't
Fourth
consider
moment,
beyond
right,
that.
right, correct, yeah.
That's my point. Is so because it can happen that, for example, when there are slight changes, so how to quantify those cases means there would be minimal changes up to fourth moment, but
And
there might be
changes
the
on
Harada changes.
Sure, that also, I mean, again, this is just a very preliminary work. We don't, as of now, I don't know how to answer that question right now, but there might be some tests which we can look up. And perform.
Okay, thanks.
I might have missed something you explained, but when you're removing these corruptions,
Mhm.
are you making some assumption on how much data you have and whether those corruptions have gone through some distribution? Because suppose all the n things are under the same cloud which stays for days.
Okay, so these n things are actually distributed over the earth. So
Okay.
I would assume it's very
Okay.
non-trivial to have a cloud that big.
Okay.
But the assumption there is that I'm obviously taking, when I'm taking correlation matrices, I'm averaging over time also. I'm time averaging. So the time averaging, the time for which I average should be larger than some time scale in the system, definitely. But yeah, that's the assumption.
So in the beginning, you said something about we are ignoring the z-axis or the line of z-axis. So you said it's not observable. Can you again explain why it is?
So if you have electric fields here and here where my hand is, and there are 3 components of it, but this electric field you can see only when it's transported along you, right? And electric fields are electric EM waves are transverse waves, so they only carry information about the transverse components and not the lateral component. So yeah.
So I guess we can stop here for the questions. Let's thank the speaker again.
Thank you.